Okay, we should have audio now. Can someone on the questions lectures channel confirm that the audio is coming through okay? Wonderful, thank you. That's great. Thanks very much. You should be able to see an announcement screen regarding the campus closure for tomorrow, the 19th of March. Can someone just give me a thumbs up that you can see that? Wonderful. Thanks very much. Good, I think we're all set. Audio levels okay? Okay, I'll assume it's all good. I'm going to mute my audio for a few minutes and I'll catch you back here at 4 o'clock for lecture start. Thanks for that. Okay, well, we should be back live, ready to go. Can someone just give me a thumbs up? They're all good. Wonderful. Thank you very much. Okay, so before we get started on today's lecture, many of you will have seen an announcement that came out from the university in the last hour that due to forecast bad weather, the Callaghan campus is going to be closed tomorrow. So that's tomorrow, not Friday, the 19th of March. So that means the entire campus will be closed. No one allowed on campus, and that's effective midnight tonight. So we have 4 lab groups, about 100 students in this class, whose assessed labs will be impacted because they were scheduled for tomorrow. So if you are one of those impacted students, we're setting up to run those labs via Zoom tomorrow at the scheduled time. And we've got some technical details to get our heads around in advance of that happening. We need to set up some separate Zoom links so you're not all crowded into one Zoom room. And I'll be providing details on those updates and links and such via our usual communication channels, Discord, but also class-wide email and Blackboard announcement. We'd like to get as many of you assessed tomorrow as is possible, realising that some of you may not be able to join in those Zoom classes tomorrow. Maybe you don't have PyCharm, for example, installed on your home computer and you rely on the university's computers. That's also okay. We'll make contingencies for plans for those. Haven't quite got my head around what we might do with those students, but the starting point for the university and also for me is no students will be disadvantaged. So my thinking is that we'll probably push those students back into next week sometime, and details to follow. I won't say any more because I don't really have the details sorted out yet. But our starting point, if you're in one of the 4 groups, either the 1 at 10 a.m. or the 3 scheduled at midday tomorrow, those labs will not take place on campus. The entire campus will be closed, and we're going to start by trying to get as many of you assessed on track as we can via Zoom, and we'll pick up the pieces with the other students that are unable to Zoom in tomorrow. We'll make plans for you. No student will be disadvantaged, and we'll do it as best we can. We're all in the same boat together. I won't be on campus tomorrow. None of us will be. Good. I realise that's probably raised as many questions as it's answered, but we need to kick off, and today's that's as good a way as any of doing it. We'll sort those technical details and get the details out to you as soon as we can. One thing we need to do though is cover the material from today's lecture, and that's what I'm here to do. We have 2 topics in today's lecture. They are one of them is a continuation of Monday's content on random numbers. You may remember at the end of Monday's lecture, in the last part, we introduced the generation of random numbers in Python. And so I'm going to show you a few applications of those today, one of which, if you haven't seen it before, might be a bit surprising to you, a bit of fun. And the second component of today's lecture is to be able to give you the ability to import data from spreadsheets. That's a really powerful thing. Lots of engineering and scientific data sets are exchanged by way of spreadsheets, both places that provide data to engineers and engineers providing data back in that form. It's really important, therefore, that we've got the ability to process data that's provided to us in that form. And so today I'll show you give you enough to get started with reading data from spreadsheets and show you a nice little example. We'll return to spreadsheet data later in the semester, and we'll look at how we might be able to write spreadsheets. But as a first instance, being able to read data in from spreadsheets gives us a lot of functionality that we can use later in the course. You'll see there's two names on today's lecture, mine and Sarah Johnson's. My colleague's Professor Sarah Johnson. She wrote the material on reading data from spreadsheets, and indeed she'll be presenting next week's lectures. So very pleased to have Sarah create the content for the reading from spreadsheets section today. So lecture overview, two main topics: using random numbers and reading from spreadsheets. We'll return to both these topics through the rest of the semester, but what we will do today is give you enough to do some really interesting and useful things. Along the way, we get more practice with the fundamentals that we've seen in the first 3 weeks of this course. Arrays for storing data, iteration using for and while loops, so doing things over and over again, using conditional code execution, so testing if certain conditions are satisfied, then executing some code, and also plotting data. And so also all these ingredients today when we're using random numbers and also reading data from spreadsheets. Now I'm conscious that, so let's start with just a recap. To generate random numbers, you may remember from Monday that there are two distinctly different ways of generating random numbers in Python. The first is to use a built-in library called random. We probably won't use that module much, if at all, and I have a strong preference for generating random numbers using the NumPy library. And so that's all I'm going to be talking about today. And unless something unexpected happens, I probably won't talk about the other method again. There are real advantages to using the NumPy libraries over and above the random library. So just to recap, you've seen this slide or the content, most of the contents of this slide on Monday. There are three distinct function calls that we can make to generate random numbers, and they allow us to generate random integers, and then to generate random float variables or floating point or real numbers. The randint function allows us to generate random integers, and we can use that, for example, to simulate the roll of a dice that's got 6 distinct outputs. We'll see another application today where we're going to, which is different from a dice. And there are two functions called random and uniform. The uniform function is really a much more general case of the random function. So I probably won't even use this random function much, because, as I said, it's a special case of the uniform function. So the two functions we are going to use to generate random numbers today are randint and uniform. So let's get started. Now, I'm conscious that some of you, indeed most of you, might not have had a great deal of experience with random numbers. And in fact, I don't really expect you to have had much experience with them at all. If you've seen them at high school, fantastic. I certainly don't expect any more knowledge than year 10 mathematics knowledge. And yet I want to be able to use random numbers and convince you that the random number generator in Python is behaving as we might expect it to do. So I'm going to rely on your intuition, and as follows. Suppose we wanted to simulate the toss of a coin n times, and n in the examples that I've got in mind here, we're going to do it 100 times, and then we're going to do it 100,000 times. And so we want to simulate the toss of a coin. We'll call it a fair coin. We'll say that heads comes up as equally often as tails. So one way we can do that, a really simple way of doing that, is to generate an array of length n, and we'll fill that array using a call to the appropriate Python function with zeros and ones, because Python doesn't know anything about heads and tails. So we'll use a 0 to represent a head and 1 to represent a tail. And so if we choose zeros and ones with 50-50 probability, we can generate an array of length n. And then we're going to display two numbers after running this function. We're going to display the expected numbers of heads we observe, and then we're going to actually count up the number of heads, the number of zeros we observe, and we'll print that out, and we'll compare the two. And we'll test and debug our code with a small n, 100, so we can see all the numbers. And then when we're confident the code works as we expect, we'll run it with 100,000 and see what happens. So just before we run the code, let's think a little bit about the expected number of heads observed. Suppose you've got a fair coin and you toss it n times. Each time it's fair. The coin itself's not weighted, and you toss it fairly. How many? If we toss the coin n times, how many times would you expect the head to turn up? 10 on 2, half the time. It's a fair coin. So you're tossing the coin, and half the time you would expect a head to come up. But there's no guarantee if we generate n random numbers, 0 or 1, heads and tails, there's no guarantee that the actual number of heads that would be observed matches the expected number. We'd expect it to be close. And in fact, if it deviated too much from the expected number, we'd think something fishy was going on and the random number generator wasn't working as expected. So we want to be able to generate the length n vec array and then display both the expected and actual number of heads observed. So here's the code. Got a new format for displaying the code. Thank you, Sarah, for working out the technical details. So here's our code, and I want to point out the key points on it here, and then we'll run it live. So you'll see that there's some color coding now, which makes it a little bit easier to see keywords and variables. There's also line numbers down the left-hand side in light grey. They're not part of the code, but they allow me to refer to lines of the code. So you'll see in line 1, we import our NumPy library. And then in line 6, we set the value of n. N's the number of times we're going to toss a coin. In this case, it's 100,000. Now, the key line here for random number generation is line 7. And so the call to the randint function in the random module inside the NP or NumPy library is called with 3 parameters. 0 to n. The third parameter is the number of times we're going to generate the random number. So that's pretty straightforward. The 0 and 2 parameters are interpreted as follows. We generate n integers in the range 0, including 0, but not and up to 2, but not including 2. So in other words, it's 0 or 1. So this right parenthesis, this round right parenthesis, means we don't include the number 2. So the only integers between 0 and strictly less than 2 are 0 and 1. So in fact, this will generate an array of length n for us, and we'll test it live in a moment. Now I want you to look at lines 10 through to 13. This is a common coding format that we're beginning to see a pattern in now, where in lines 11, 12, and 13, we run the loop index I over every single index in the array. And then we have a conditional statement if xi is equal to 0. So that means if the ith element of the array is equal to 0, we increment the number of heads we've counted. So this head count plus equals 1 is a shorthand for head count is assigned the value of head count plus 1. So it increments the head count. And in order to do that, we need to have initialized head count, which we do here in line 10. So after a while, and I suspect many of you are starting to see the pattern already, this is a really common coding pattern where we initialize the value of a running sum, in this case head count, and then we run the index over the range of all the indices of the array. Then we check a condition, and we sometimes update the head count and sometimes not. In this case, we update it only when we've rolled a 0. And then we can print the number of the data that's required. The expected number of heads, as we talked about before, it's half n. That's the expected number of heads we'd expect to see, and the observed number of heads, the actual number of heads, is simply the head count. So let's now run that live and see what happens. Here's our program, and it's exactly the code that you've seen in the lecture slides. I've literally cut and paste, and now I'm going to go back and just bump that down to 100 before we run the program. Heads and tails. We run it. Now, what you see down the bottom is the vector of 100 ones and zeros. That's why I printed it out, and you can see that. So that it's not very informative, but you can see there's a random pattern of ones and zeros. There's no obvious patterns in there. The expected number of heads is 50 because n was equal to 100. So we'd expect half the rolls to come up with a head. And indeed, the number of heads observed in this run was 49. Let's run it again and see what happens. Run the code again. We get 51 heads this time. Let's run it again. We get 49 heads this time. Let's run it again. See if I can run it again. We get 45 heads this time. Run it again. 50 heads, right on the expected number. Run it again, we get 43. So you can see there's variability on every run. If we were to get no heads or one head or a really small number of heads, we'd expect something fishy was going on with our program. But in fact, that the random number generated in PyCharm in Python's a very good one, and so the program's operating as we expected. So there's our first example. Use of an array, iteration, conditional execution, and importantly, the creation of this, the accumulation of this running sum that counts the number of heads we've observed. And it worked. Oh, we didn't run it for 100,000. Let's do that. Let's do that now. We've missed an opportunity. Go back and now run it for 100,000. Takes a bit of time this time. Oh, there we go. 50,000. 50,000 was expected number of heads, and we actually observed 49,988. Run it again, and we get a different number of heads each time. Sometimes bigger, sometimes smaller. If we're lucky enough, we'll see exactly the expected number. So there we go. Good. That was our first use of random numbers. Random integers, in the simplest case, 0 and 1. Let's look at an engineering application now, a little bit closer to something we might find in an engineering course. Suppose we've got a situation where we're manufacturing steel bolts, and the manufacturing process is imperfect, and it makes these bolts with a length that's somewhere between 17 and 19 millimeters long. But within that range, the bolt can be any length with equal probability. But even though the manufacturing process can make them in the range 17 to 19, a more restricted range is regarded as acceptable. Is within engineering tolerance and the acceptable tolerance. So the goal here is to write a Python program using random numbers, which generates a large number of simulated bolt lengths, and then calculates the fraction of bolts which are in the acceptable range. If you think about it, the bolts can be anywhere between 17 and 19 mil, but the only acceptable ones are between the range 17.25 up to 18.75. So this is similar to the previous example where we tossed a coin. But this time we're generating not integers, but floating point numbers, because the bolts can take any real valued length in the range 17 to 19 mil. So we need to use a different Python function in order to do that. But nonetheless, it's reasonable. It's got commonality with the previous example in that what we're going to do is estimate the number of acceptable bolts, or the fraction of them, the percentage of them, by counting up the number that are in the acceptable range and dividing that by the entire range. So the acceptable range is anywhere between 17.25 and 18.75 mil. And that's only a certain portion of the manufacturing tolerance, which is anywhere between 17 and 19 mil. then we express that as a percentage, so multiply it by 100. In this case, the expected percentage of acceptable bolts is 75%, because the difference between these two numbers as a fraction of the possible length is 3/4. So here's our code. In some ways, it looks quite similar to the previous example. We set up to generate an array of n random numbers somewhere in the uniformly distributed in the range 17 to 19. So the uniform function here is key. That's Python's, or the NumPy library's, random number generator that's uniformly distributed. So it doesn't bias the numbers anywhere in the range. It just says the numbers must be somewhere in the range 17 to 19, and all numbers in that range are equally likely. Numbers outside that range never happen. That's one particular probability distribution. And we generate n of them. In this case, we're setting up to generate 10,000 of those random numbers and put them in an array of length 10,000. And then I've coded in line 6 and 7 the tolerance of what's acceptable, what's the low to high range of the acceptable range for these bolts. And again, see the coding pattern? It's very similar to the previous one. We have it in lines 11, 12, and 13. We have the loop counter ranging over the complete set of indices for the array. And then if the random number that's located at that ith location falls in the range low to high, including both the high and low values, so we've got a less than or equal to, less than or equal to, then we update the number of good bolts, or the count of the good bolts that we accumulate as a running sum. Good count plus equals 1. In other words, good count is assigned the value good count plus 1. And we need to initialize that. So we've initialized it here that in line 10. And then the percentage of parts that are within tolerance is the good count, namely the number of bolts that have fallen in that range between low and high, divided by the total number that we drew, and then multiply by 100 to express it as a percentage. So let's run that now. Engineering tolerance. And here's our code. Just for good measure, let's bump that number down from 10,000 to 100 and then run that code. Let's print our X value this time. So it's a longer vector, because it's a longer array, because it's got 100 entries, and all of them are floating point numbers. All of them are floats. So we can display them. And in this case, if we look at that array of 100 numbers and only count up the values that are within range low to high, or between 17.25 and 18.75, we get 74 out of those 100 fall within that range. So if we run the program again, this time we get 81%, so 81 out of the 100. Run it again, this time 77 out of the 100, or 77% are within that range. So again, really similar to the first example, except now we're using floats rather than ints. So let's bump that up now to 10,000 random numbers, run the program again. This time we've got, if we ask Python to print the array of 10,000 numbers, it says, I'm not doing that. That'll take me too long to do that. It'll take up too much screen space. It'll be too slow. So what it does, it prints the first 3 numbers, ... and then the final 3 numbers. You can always interrogate the values that are inside that array by indexing them through this square bracket, but we don't need to do that. All we need to do is store the values, run through the indices, and keep a running sum of all the values that fit within the acceptable range. So really similar to the previous example. The big difference though is that these are floats, not ints. So the function is uniform rather than rand int. Okay. Now let's step it up a bit. Let's look at an example that's a little bit different and allows us to graph these random numbers. We haven't seen them. We've only seen them printed out so far. So what I want you to do is imagine we've got a circular dartboard. It's got radius 1 meter, so it's a pretty big dartboard. I want to keep the numbers simple. So the dartboard is circular with a radius of 1 meter. And that dartboard is located in the middle of a square. It's centered on a square. And the side edge of the square is 2 meters. These numbers have been deliberately chosen. Now we go through the process as follows. Suppose we throw darts uniformly, randomly, at the dartboard. Some of them fall within the circle of the dartboard, some of them don't. But all the darts fall somewhere within the square that's of 2 meters on edge. So it's a little bit artificial, but we're going to throw the darts at the dartboard. Some of them will fit somewhere within the circle. Great. Not all of them will, however. Some of them will fall outside the circle, but all of the darts, you throw a dart, it goes somewhere in a square of 2 meters side where the dartboard is centered inside that square. So if you want to get an image, it's a circle that fits neatly inside a square. So it's just the circle's just tangent to the edge of the square. So it fits nicely. It's circumscribed by the square. Now, here's our challenge. I want to write a Python program which simulates this throwing the darts for n times. And if the dart falls within the circle or also on the edge of the circle, the dartboard, I want to put a red dot on the screen. And if the dart falls somewhere outside the circle, but in the square, I want to put a blue dot. And just a reminder, I want to write a program which does that. So we've got to distinguish between points. I call it inside the circle, but what I mean is inside or on the perimeter. So going forwards, inside means possibly on the edge. Points inside the circle satisfy this mathematical equation towards the bottom of the screen. X squared plus y squared is equal to 1. So I'm really using coordinates X and Y for the horizontal and vertical coordinates. So let's think about how we might do that. We need to be able to throw a dart and then have its location, the point that it hits the wall, represented as in X, Y coordinates. And I said before that the square was 2 meters on edge. So what we're actually going to do is generate our random numbers as being uniformly drawn from the range -1 to 1. So our dartboard's going to sit right at the origin of our axes. And the X coordinate of the dart is going to be drawn from -1 to 1. So it can fit anywhere between plus or minus 1 meter horizontally. And the Y coordinate, similarly, somewhere between plus or minus 1. So if you're having trouble visualizing this at the moment, in a slide, I'll show you what it looks like. Now, in this case, we're generating 10,000 of these pairs. So using lines 1 through 8, we create 2 arrays, an X array and a Y array. They're each of length n, and each element of the array is a float. And that float has been randomly chosen between plus or minus 1 in both the horizontal or X-axis and vertical or Y-axis. So now lines 10 through 15 set up a loop ignore line 10, doesn't need to be there. Lines 11 through 15 set up a loop where we run across the range of the loop indices, and then we decide, are we inside the circle or are we outside the circle? If we're inside the circle, we put a red dot. Hence, in line 13, plot with an R dot. And we're plotting the X and Y coordinates, horizontal and vertical. Line 15, we plot a blue dot. So if this inequality in line 12 is satisfied, line 12 of the code corresponds exactly to the mathematical equation at the bottom of page 8. So we run across the indices. If the inequality is satisfied, the dart must have fallen inside the circle. We put a red dot. Otherwise, we put a blue dot. And we plot those results. Let's do it. See what happens. This is a fun one, this one. Here's the code. You saw I said inside count. That's actually part of the next example. So I'm going to delete that line of code. It doesn't exist. It's not necessary. And now I'm going to run it with n is equal to 100. Oh, sorry. Run dartboard. Here we go. There's dartboard. 100 points. And both the X and Y coordinates are constrained to be in plus or minus 1, in the range plus or minus 1. There's nothing obviously circular going on here, but there are 100 points. Let's run that code again, except this time we'll put not 100 points, but 1,000 points. Looks a bit more circular now. So remember, the blue points are outside the circle. The red points are inside the circle. We can run that again. Okay, you can sort of, if you squint your eyes, you can sort of see points that are terribly far away from, greater than a distance of 1 from the origin, and the origin here is at the 0 right in the middle of the square. They get a blue point, a blue dot. Otherwise, they get a red dot. Let's run it again, this time for 10,000 points. That was 1,000. Let's make it 10,000 points. Run the code again. Takes a little while. It's the plotting that's taking the while rather than the generation of the random numbers. And now we get a really nice pattern observed. It's clear now that the circle of radius 1 that fits neatly inside the square of edge size 2 is really being picked up by this random number generator. Both the X and Y coordinates necessarily fall between the range plus or minus 1. You can see that with the axis limits here, between no point sits outside the square with the vertices at plus or minus 1. And it's whether a point is red or blue has simply been calculated based on this inequality here in line 12 of the code. It's whether the X squared, or the ith component of the X array squared, plus the ith component of the Y array squared, if it's less than or equal to 1, that's all that determines whether a red dot or a blue dot has been generated. So there you go. We've simulated a dartboard. and we've made an interesting use of uniformly distributed float numbers between plus or minus 1. And here's the explanation for it. We're generating the length n arrays, x0 through xn minus 1 endpoints, and likewise for y. If the ith component, where the xi is strictly in the range plus or minus 1, and likewise for yi. So the dot that we put x and y is determined by the ith component of the y and of the x and the ith component of the y arrays. There you go. And so now if we that was n equals 100. This is n equals 1,000. This is n equals 10,000. So you can really see both the n equals 100 and 1,000 cases are working. It's just not obvious what they're doing, but it's clear now what's going on. Let's look at how we might be able to apply that. We're going to use a very small modification of this code that you saw on page 9 to estimate the value of pi. That sounds a bit odd. How are we going to do that? First, we're going to modify example 3 to count the number of points that are inside or possibly on the edge of the circle, on the perimeter. And then we're going to somehow use those results to estimate the value of pi. How do we do that? Well, here's our strategy. The area of the square in which all the darts must fall is 4. The area of the square that you see in the bottom right-hand corner of page 10, the area is 4 because both the x and y coordinates are constrained to fall within plus or minus 1. The edge length of the square was 2. 2 times 2 is 4. The area of the square is 4. The area of the circle, if you think back to high school mathematics, the area of a circle is pi r squared, where r is the radius. And in this case, the radius is 1. It's 1 because the radius fits just neatly inside half an edge length of the square. So that must mean that the area of the circle, which is a fraction of the area of the square, so this figure that I'm calling uppercase R is the area of the circle divided by the area of the square. It's the area of the red circle divided by the total area of the in which the circle sits. That's equal to pi on 4 because the area of the circle was pi and the area of the square is 4. So that ratio of the area of the circle to the total area of the square in which side the circle sits is pi on 4. Now pi is about 3.141 something. Let's call it's about 3. Really roughly pi is about 3. So that means this ratio of the circle area to the total square area is about 3 on 4, which means which looks about right. This circle is occupying about 3/4 of the space available to it in the square. The precise fraction is not 3 on 4. The precise fraction is pi on 4. So how do we use that with a modification of example 3? Well, if we look for large n, let's look at the example, the figure we see on page 10. If we count the number of points that are red, namely the number of points inside the circle, and we divide that by the total number of points or the number of darts that we threw, then we get an estimate of R. And if we can estimate R, then we can estimate pi because the estimate of pi is just 4 times the estimate of R. So we can estimate pi by counting the number of points in the circle and dividing that by the total number of points that we draw. And here's our code. It looks really similar to code in example 3, which is why we had this carryover of inside count. Let's do it. We've got 10,000 numbers. We store them in 2 arrays, an X array and a Y array. We then loop over the range of indices in line 11. if the drawn point or the dart position is inside the circle, we put a red dot and we update the number of points that are located inside the circle. So inside count's going to count the number of red dots. And if we're going to keep a running sum, we better initialize it, and we do here on line 10. If the dart falls outside the circle, we don't update any counts, but we do put a blue dot. And then our estimate of pi is 4 times the estimate of this uppercase R, which was the number of points that fell inside the circle divided by the total number of points. So if we run that code now, let's run this code. Here's the code. It's exactly the code that I showed you on page 12. Let's run this code now. It's going to do 2 things. It's going to produce a plot and an estimate of pi. It's actually generating 20,000 random numbers and then plotting those 20,000 random numbers. So there's our plot. We've seen that before, so I'll just move it off to the side. And our estimate of pi is 3.1432. That's not bad. 3.14159. That's pretty good. It's accurate to 2 or 3 decimal places. Let's run it again. Run it again, we get a different set of random numbers. So we'll get a different estimate of pi. We get a different plot, it'll look similar, and we get a different estimate of pi. This time it's just a bit above the actual value of pi. So how good's that? When you came to uni today, do you expect to be able to estimate pi by drawing random numbers? Now there are much better ways of calculating pi accurately than this example. But there are methods that are cutting edge in statistics and its applications right through all branches of engineering, which do in fact use the generation of random numbers to compute quantities that are otherwise really difficult to compute. So there are better ways of computing pi, but they're called Monte Carlo methods, meant to be like the casino. They're Monte Carlo methods that are used to estimate quantities that are actually really difficult to compute using any other method. And so there we go. Okay, we've got about 15 minutes to go. Second part of the material, we'll probably work through a bit faster, but I'll also make the point that you'll get a chance to experiment with the exact code and the data set that I present here in this example. You'll get a chance to work with those in next week's lab experiment, lab assessed, unassessed, not assessed, the next week's lab. So far we've been working with really small problems, or problems that have used small data sets, 2 or 3 parameters to simulate the height of a soccer ball being kicked. But often engineers work with really large data sets, and those data sets come in many shapes and forms. And if you're an engineer working in an engineering firm and a client gives you a data set in a particular format, it's your role to be able to work with that data set, not ask the client, can you give it to me in a preferred data? Got to deal with data in all different shapes and forms. And there's a wonderful package available in Python called Pandas that allows us to import data in all sorts of weird and wonderful formats. And we can import it, the package into Python just like we do NumPy and Matplotlib. So the line 1 that you see at the bottom of the page here, import pandas as PD. So that allows us to make use of the functionality that comes in this external library. You may need to do a pip install pandas. We'll work with that next week in the lab. So as I said, there's many different data formats. The only one I want to talk about or use today, I don't want to talk about the actual format as much as use it. there's a format called CSV format, which is pretty much the most straightforward data format that's available. It stands for comma separated values or comma separated variables. And once we've imported the Pandas library, line 1 here, reading a CSV file is as simple as line 2 here. My data is equal to PD, pandas, dot, and then make use of this, this read CSV function inside the Pandas library. So it's simplicity itself. Now, the version of the import statement or the read CSV function that you see on page 14, at the top of page 14, assumes that your CSV file is in the very same directory as your Python code. If that's not the case, then you need to you can specify the full path name of where that file is located, and so you can again use the PD, the read PSV function inside the Pandas library. You specify the full file name, and again, the principle's straightforward. The details are a bit fiddly, and I'll let you work on that in the lab next week. But that is really simple. One import statement and one read statement brings your data into Python. Unfortunately, the my data format is not quite in the format that we want. And so we're going to have to do one more line of processing to get it into an array, and that'll come on the next slide. Once we've imported the data, it's always good to check that it matches up with the data that we can see in a spreadsheet, for example. And so this function that you see here on line 1 towards the bottom of the screen, this mydata.head is will show the first few lines of a data set. Sometimes you import data sets and they might be gigabytes. You don't want to see all of it, but you just want to see the first handful of lines in the data set to confirm that it actually is the data set that you think it is. So we'll actually do this live in a moment, but I just want to point it out to you here. The mydata.head function inside the Pandas library allows. So my data is this thing called a data structure I've referred to up here. We're not going to talk about data structures, or probably won't talk about them in this course. There are whole university courses on data structures. We'll be comfortable that we can just read data into something called a data structure. And then in the next line, next page, I'll show you how to convert that data structure into an array. And once we're in an array, we're off and running. We can do what we want to be able to do. So the my data, we apply the head function to it, gives us the first few lines of the data set. And here it is, page 16. Once we've imported the data into something called a my data structure, then we use this particular syntax here in order to actually extract the values of interest. And this is really nice, this line of code that you see here on line 1 in the middle of the screen. It's really nice because you know how in spreadsheets you've got you can have multiple columns and each column's got a column heading. You can read data out of a spreadsheet and then pick off one column at a time based on the title of the data that occurs in the spreadsheet itself. So the line that you see here, the line of code, my column is equal to my data column name dot values. That's the way to tell Python that I want an array of data, and I want the array of data read out of the spreadsheet, and I only want the array of data who's corresponding to the column with title column name. So you can have a data that's got hundreds of columns. You want to read out one column at a time. You just have to identify the column with its name and read it into Python in this way. And once we've got data in an NumPy array, we're off and running. We can do stuff with it. And we're going to look at an example right now. So this is a really good example, real data, and we're going to process it for you live. And again, you'll get a chance to work with this data set and this program in next week's lab. So suppose we've got a data set called rainfall.csv. It's in a comma separated variable form, and it records annual rainfall for 20 different regions over the last 10 years. And so we've got the data in a 2x2 grid, spreadsheet, if you like. And the column headers give labels to the regions. I said there are 20 regions. They're labeled A through T. And columns B, C, D, E, F, and G are the rainfall in particular years. Years 2010, 2012, 2014, 2016, 2018, and 2020. So every second year, we've got the rainfall, the average rainfall, annual rainfall, the total annual rainfall for the 20 regions identified through rows 2 through 21. And the problem that we are set is that we'd like to know how many regions have seen a reduction in rainfall between 2010 and 2020. So these are the first and last years in this data set, columns B and G in the spreadsheet. So the question is, how many regions have seen a reduction in rainfall between 2010 and 2020? So before we see the code, let's just reflect. Let's just think about what sort of operations we'll expect to see in the code. We need to be able to read the rainfall in corresponding to years 2010 and 2020. So we're going to be able to read in the column whose title is called Rainfall 2010 and the column whose title is Rainfall 2020. Now, normally we would refer to those as columns B and G in a spreadsheet. We're not going to do that here. We're going to identify the columns not by their column label in Excel, but their column title in the spreadsheet itself, Rainfall 2010 and Rainfall 2020. So the question is, how many regions have seen a reduction in rainfall between 2010 and 2020? First step, let's read those rainfall figures into 2 separate arrays. And then we need to count the regions that have seen a reduction in rainfall between 2010 and 2020. So we're probably going to see a loop that runs over the elements of the different regions. So we're going to run down the column and compare the numbers in the 2010 and the 2020 columns. So in words, before we see the code, we'd run down and compare the 67 with the 65, the 74 with the 74, the 75 with the 60, the 76 with the 61, the 77 with the 62, and so on. So we're going to have to set up a loop that runs through, and we're going to be comparing pairwise comparison of those 2 arrays. So let's do it. The code here is split across 2 screens so you can see it, but it's actually one file, and we're going to run that file live for you in just a moment. So we import Pandas as PD. We saw that before. In line 4, we read in a data structure called rainfall data using the read CSV function inside Pandas. And here's the name of the file, rainfall.csv. And so because of this particular syntax, we're going to have to, the program is going to assume that rainfall.csv exists in the same directory as the code itself. And then we're going to print the rainfall head, rainfall data head, which means print the first few lines of that data set. And then we're going to, in lines 8 and 9, extract the columns corresponding to the 2010 and 2020 calendar years. And then after lines 8 and 9, we'll have the rainfall data that we want in 2 separate Python arrays rather than 2 columns of a spreadsheet in Excel. Now we need to calculate the number of regions that have seen a decrease in rainfall. So line 2 of this code here gives us the number of regions. And rather than reading it directly from the spreadsheet, we calculate it by the length of the array. and then lines 3, 4, 5, and 6 run through the array indices. And every time the rainfall in 2020 is less than it was in 2010, we update the count. So again, this is a really common programming pattern we're seeing now. Indices running over a range. If a condition's satisfied, update a count. We've seen it 3 times today. And then we do some processing. The percentage decrease is the total number of regions that saw a decrease divided by the total number of regions multiplied by 100 and then displayed in a percentage format. So let's run that live, and then we're just about good to wrap up. Here's our code. It's about 20 lines. These 20 lines are exactly the code that you saw in the lecture notes, just that was split across 2 pages. So let's run that code now. It's called Pandas CV and Pandas CSV. Okay, so the first thing we see highlighted in blue is the result of the head function, which prints the first few lines of the data set. It also produces not the whole data set, but the first 3 columns and the last couple of columns. The only ones of interest to us are the columns identified by rainfall 20 and 2010 and rainfall 2020. And then, having processed, we found that of the 20 regions, 13 have reduced rainfall, which is 65%, and we're done. So a relatively simple processing task, count the number of regions that experienced a decrease in rainfall, although a really useful thing to be able to do, to be able to read data from a spreadsheet. So we're pressing hard up against our 5 o'clock limit. So we've seen 2 things today. We've seen generation of random numbers, random integers, random floats, and we used random floats to estimate pi. Imagine throwing darts at a dartboard. And then we introduced something really powerful, being able to read data from a spreadsheet. You'll get a chance to practice both these in the lab next week. I'll leave it there, but we'll be in contact because while lectures will resume as normal on Monday, Callaghan campus is closed tomorrow, and so we need to be working away to set up those 4 lab groups that have their assessed lab tomorrow to make sure that they're catered for. Be in contact via Discord, email, and Blackboard. Until I see you next time, bye for now.